All right. Question 5 last year dealt with finding area and volume. Pretty sure, in fact, I'm going to guarantee this is not going to be on the test this year because they said they're only going to cover the first 75%. They're not going to cover applications of integrals, and that's exactly what this is. But we're still calculus. I don't care about the AP test 100%. I care about it a lot. But I also care about you just learning the calculus, especially those of you who are planning on taking calculus in college, those of you who plan on taking BC next year. It's important that you are still able to practice this. So you should still practice this problem just because it's calculus. But keep in mind, it's not going to be on the AP test. Part A is asking us to simply find the area of the shaded region. We've got g of x and we've got h of x, but they didn't tell us which function is which. They didn't tell us which one's g and which one's h. It's up to us to figure out. And we don't have a calculator, so it's not like we can graph it. One thing that we could do is we can just look at the functions themselves. Hopefully we recognize that h of x is simply just a parabola. So if I look at the two functions, that top function is parabola. The bottom function, notice it kind of parabola, but then it curves back around again. That can't be a parabola. That's way more of a cosine graph than anything else. Another thing that you could do if you plug in 0 into both of these functions, when you plug 0 into g of x, you get 1. When you plug 0 into h of x, you get 4. So we can clearly see which one is which. So just to highlight them, g of x in yellow, that's the cosine graph, that's this one, and then h of x in, let's go blue. H of x is the top one. That way we've got Michigan colors. Yay, go blue. So now that we know which function is which, we can find the area of R. This is something that we practiced. This is the straightforward, easiest part, although this is the part that does require the most work out of the 3 parts in this problem. We have to find the whole area, and area is simply just the integral of the top graph minus the bottom graph. We can clearly see that this graph from the x value starts at 0 and ends at 2. Our top graph, as we mentioned before, is h of x, and our bottom graph is g of x. When you're doing this, you could just put h of x minus g of x here to start. We're actually going to need to put the functions in there because we actually have to integrate them, but for now, I'm just going to put it in there like that. So if this were a calculator problem, you wouldn't bother writing out the actual functions. You could just do that and then type on your calculator and get the answer. Unfortunately, this is not a calculator problem, so we have to go through and do all of the work. So let's get those functions in there. Integrating from 0 to 2. H of x is 6 minus 2 times the quantity x minus 1 squared. And from that, we're going to subtract g of x. So when I subtract g of x, you should subtract it in parentheses or distribute the negative sign right away. I'm just going to distribute the negative sign right away. So that minus 2 is going to become plus 2. And the plus 3 cosine will become minus 3 cosine of pi over 2x. Now, this is quite the integral to have to solve. It's not terrible. You do want to break it apart because technically there's at least one u substitution that you have to do that you can't just ignore. There's one u substitution that if you don't do it, it's not going to harm you, although you should always do the u substitution, right? So I'll just integrate each one of these. There's 1, 2, 3, 4 different terms here, right? The 6, the parentheses squared, the 2, and the cosine. So we're going to integrate each one of those individually. So first, the 6 is no problem at all. That's just going to integrate to be 6x. Then the minus 2x minus 1 quantity squared. That technically needs a u substitution because it's x minus 1 quantity squared. But when you do that substitution, you would let u equal x minus 1, and so du would just equal dx. So you wouldn't have to worry about that u substitution. If you forgot about it, you don't gain any constants in that. So when we integrate that, that's simply going to be, oops, get the right marker, that's simply going to be minus 2/3 times the quantity x minus 1 cubed. I can stop and check that real quick if I were to take the derivative. 3 times negative 2/3 is negative 2. We subtract 1 from the power, we get x minus 1 squared. And then we do the chain rule. We'd multiply by the derivative of x minus 1, which is just 1. So everything matches up so far. Then if I keep integrating, the integral of 2 is just 2x, so that'll be plus 2x. And then finally this integral you definitely need to do a u substitution on because we have this pi over 2x. Now whether you do that u substitution on paper or in your head, doesn't matter, but you need to do it. And so if we look at cosine, the integral of cosine is sine, and so we're still going to be negative. It's not the derivative, it's the integral. Like I said, the integral of cosine is going to be sine, so we're going to have a sine. The argument is not going to change. It's still going to be pi over 2x. But if we do u substitution, we would be letting u equal pi over 2x, and that means that when we do the du portion, we would be getting a 2 over pi that we would need to multiply by. And so with the 3 that was currently out there, we'd end up with 6 over pi. If that's something that's confusing to you, write out the u substitution. This is what you should get. And we're going to evaluate this from 0 to 2. And so from here, you're just going to plug in, plugging in 2 into all of this, and then plugging 0 into all of this. If we plug 2 into all of this, you're going to get 12. 2 minus 1 is 1, cubed is 1, times 2/3 is 2/3, so 12 minus 2/3. Plugging in 2 for the 2x portion, 2 times 2 is 4. And then finally plugging 2 into the sign argument. If we plug 2 into the x, 2 times pi over 2 is just pi, and the sign of pi is 0. So regardless of any of the rest of that, that's just going to be minus 0. So that's what we get when we plug in the 2. Minus, now if we plug in 0, this becomes pretty quick. 6 times 0 is 0. 0 minus 1 is negative 1. Cubed is also negative 1 times negative 2/3 will make that plus 2/3. 2 times 0 is 0, and then when we plug 0 in for x in the sign argument, we get the sign of 0, which is also 0. So while we didn't have a calculator to do this, a lot of stuff worked out really, really nice. And so if you put that all together, you should end up with a final answer of 44 thirds. Point values for this problem. You get 1 point for simply knowing how to find area. That's a point every single one of us should have. You get a point for integrating the g of x correctly or h of x correctly, and a point for integrating the other one correctly, and then you get a point for the right answer. So lots of easy points here because area was not a difficult topic for us. If we tested on it, I'm certain that we would have really, really rocked the area portion. It's the volume that tends to get us trip us up, and the volumes here aren't that bad, that we'll see in a second. But there's 4 points right there for you. Part B. Remember when we did volume, there was 2 ways to do volume. One way was to rotate, and the other way was knowing the cross-section, and that's what this part is. Region R is the base of a solid, and each cross-section perpendicular to the x-axis has an area that is equal to 1 over x plus 3. So I didn't even need to figure out what the area is. When we did these, it was the area cross-section is a square, and we had to figure out the formula for the area of the square based on x's, or it was an equilateral triangle, or a rectangle where the length was 5 times the width, that sort of thing. Here, we don't have to figure anything out. They gave us the area formula. That makes this part even easier. And many of my students last year had no problem with this part because they set it up so easily. We're trying to find the volume. We know based on the things that we've done in class just recently that volume is going to be the integral of the area formula. And since it's cross-sections perpendicular to the x-axis, we know it's going to be dx, so our limits of integration aren't going to change. They gave us our area formula, 1 over x plus 3, and dx because it's perpendicular to the x-axis. Well, that's not bad at all. In fact, that's probably one of the easiest AP problems I've seen in a long time. I have to integrate 1 over x plus 3. Technically needs a u substitution, but it's going to work out to be the natural log of x plus 3. Technically absolute value, but it's not going to matter in this problem because of the values that we have. And we're going to evaluate that from 0 to 2. And so then if I simply plug in those values, plugging in 2, we'll have the natural log of 5. Minus plug in 0, we have the natural log of 3. You could leave your answer like that, or you could do your logarithm rules and put it together and write it as the natural log of 5/3. Both of those answers are acceptable. You do not have to write it as the natural log of 5/3 if you don't want to. I wouldn't, because if you start doing properties and you're not 100% sure and you do something wrong, you lose a point. But if you leave it as natural log of 5 minus natural log of 3, you're guaranteeing yourself the points, and that's most important. Where points come from, you get a point for knowing what you have to do and a point for doing it correctly. That's about as straightforward as it can be. Finally, part C, we have to write but don't evaluate. Remember I mentioned this before we left, that they tend to do this a lot. We simply have to write the formula that would give us the volume of the solid generated when we revolve this area about the line y equals 6. So the line y equals 6 is somewhere, let's see, that's 4, that's 5, that's right here. There's the line y equals 6. We're going to take this area and revolve around that line. So First thing that we want to realize is whether this is dx or dy. We are revolving around a line that is parallel to the x-axis, so parallel to the x-axis means that this is going to be dx. So when I set up my volume formula, I know I need a dx in there. I also know I'm rotating. Rotating always requires pi, so I'm going to get that pi on the outside right away. Because I know that this is dx, my limits of integration from part A and part B are not going to change. What I am going to do, though, is I'm going to move this over just a little bit because I'm realizing I'm not going to have a lot of space. So let me start just a little further over to the left. There we go. So our volume is going to be pi times the integral from 0 to 2. And now we just got to find our radius or our radii. If we go back up to the picture, we can see that the area does touch the axis that we're rotating on, but the area doesn't always touch it. It does touch it technically at one point. It just touches it right here. But there are other spots like here where it's not touching the axis of rotation and here where it's not touching the axis of rotation. Those little areas are going to cause us to have a donut. And so I know that this thing is going to be a donut. That's really, really important. When I have a donut, that means I'm going to have two different radii that are going to be squared. So when I try and figure out those radii, no problem. We did this in class. This was a stumbling block for many of us. And so it's a good thing that we're taking a look at it again. So the radius, the big radius, we always start from the axis of rotation. Our axis of rotation is the line y equals 6. So starting from there, we're going to go all the way through the graph until we get to the edge of the area. That's that distance right there. So we're looking for the red line distance. That'll be our big radius. And then the little radius will be from the axis of rotation only to the graph itself. I don't want to do it where it actually intersects. I want to do it like, say, over here. So that line, that's kind of hard to see because of the highlight, but that little itty bitty blue line, that's going to be our small radius. So we just have to figure out what those radii are. If you practiced these back just a few weeks ago when we were practicing this stuff, remember how to figure out those lines. Those lines are simply just top graph minus bottom graph. And so for our big radius, the top graph is the line y equals 6 minus the bottom graph. The bottom graph is g of x. Because they define g of x, you don't actually have to write up the whole function g of x. You can just write g of x. And we are going to square that because it's a radius. That's our big radius squared minus the little radius squared. If you get the big radius, you get the little radius for free, or vice versa, because they always work the same way. If we look at that blue line again starts at the line y equals 6 minus the bottom graph that creates that line is the function h of x. So that's going to be 6 minus h of x, quantity squared. Notice my two radii look exactly the same. 6 minus f of x, 6 minus g of x, and 6 minus h of x. So that's always going to work out that way. So even though you're not tested on this, that would have been a really easy problem for us. As far as points are concerned, we only get a couple of points here. We get 3 points. We get a point for having the pi and the 0 to 2. We get a point for recognizing that this thing is a donut. So as long as you have 2 radii squared, you get a point for the donut recognition, and then you get a point for having the correct radii. There we go. So there's your points for this one. Not too bad. Again, this is simply for you to practice because I want you to know calculus. This is not going to be on the AP test this year because this part is not covered. Until next time.